All right, let's dive in. Today, we're going on a pretty incredible journey, from a simple handful of sand all the way to the powerful brains sitting inside your computer. Let's get into how a CPU is actually made. So it really all starts with a puzzle. What could a sandy beach possibly have in common with a massive, complex supercomputer? They seem like they're from completely different worlds, right? But believe it or not, they share the exact same fundamental ingredient. And the answer is silicon. Yep, the sand on our beaches is mostly silicon dioxide. So in this explainer, we're going to follow the amazing journey of that simple element as it gets transformed into one of the most complex things humanity has ever created. Okay, so our journey begins with the very first, and maybe one of the most critical transformations, turning that raw sand into a material that's almost perfectly pure. The whole process starts by melting down purified sand in something called a crucible. From that molten silicon, a huge, perfectly structured single crystal is slowly, carefully grown. The result is this, a monocrystalline silicon ingot. And get this, it's 99.99999% pure, which makes it one of the purest materials we have ever made. So now that we have our perfect crystal, the next step is to get it ready. We need to create a totally flawless canvas for all the microscopic circuits we're about to build on top of it. That giant ingot is sliced with incredible precision into these thin discs we call wafers. Each one is less than a millimeter thick, and it's polished to an absolutely perfect, mirror-like finish, totally free of any junk or contaminants. This perfect surface is so important, because we're about to work on a scale where a single speck of dust would look like a giant boulder. All right, we have arrived at the absolute heart of making a CPU. It's called photolithography. You can kind of think of it like a super high-tech, microscopic version of photography where we're going to use light to literally print billions of circuit components. This whole process is kind of like making a microscopic stencil. First, the wafer gets coated in a special light-sensitive chemical. Then, UV light is blasted through a mask, which is basically the blueprint of the circuit. Where the light hits, the chemical hardens. After that, all the unexposed, soft parts are just washed away. Then, chemicals are used to permanently etch that pattern right into the silicon. And that right there creates the very first layer of our circuit. But here's the thing. A CPU isn't just a flat drawing. It's a really complex, three-dimensional city of interconnected circuits. So what we just did, that was like laying down the first street. Now, we have to build the skyscrapers. And this is where the complexity just goes through the roof. That entire 5-step photolithography process we just talked about, it gets repeated more than 50 times. With every single cycle, new materials like copper are added, creating these incredibly intricate layers of wires and transistors. It's literally like building a city with billions of individual components, all packed onto something that can fit on your fingertip. So, after building this entire microscopic city, we have to make sure every single part of it is perfect. At this scale, the tiniest little flaw can cause a complete failure. So it's time for some serious quality control. Each potential CPU on that wafer is called a die. Tiny automated probes come down and run a whole bunch of electrical tests on every single one. If a die passes all the tests, it gets marked as perfect. But if it fails even one of them because of some tiny flaw in one of its billions of transistors, it's marked as defective and gets tossed. There is just no room for error. And this brings us to this really important concept called yield. As you can see here, even in the very best factories, not every chip comes out perfect. A typical yield is around 80%, which means 1 in 5 chips on this super expensive wafer is just discarded. Trying to maximize this yield is one of the biggest economic puzzles in the industry because it directly impacts the final cost of pretty much every device you own. Okay, so we've got a wafer that's full of tested, working chips. The final stage is to free them from their silicon home and give them the body they need to survive and do their job inside your computer. So now we get to the final assembly. A diamond saw comes in and carefully cuts the wafer into all those individual dies. Each working die is then mounted onto a substrate, which is what lets it connect to the rest of the computer. A metal cap goes on top to protect it and to help keep it cool. Then, after one last super intense round of testing for performance and power, the CPU is finally ready to go. So, from a single grain of sand to a finished computer chip, it's just an incredible feat of engineering, and it's happening millions of times every single day. And that leaves us with this one big question. As we get better and better at building things at this almost atomic level, what new amazing things will these tiny brains make possible for our future?